Good morning, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm your host for today's session. And before I introduce our guest speaker, as we're in the habit of doing, we'd like to run a couple poll questions just to get some preview of what your perspective is on the topic and give you a chance to give us a little bit of feedback. There's no obligation or liability, strictly just trying to understand what your perspective is on today's topic. So if you would please indicate kind of what your stance is on being aware of Class C and D special purpose ground fault circuit interrupters. For those of you attending today, make sure we've got your email address correct because that's used to provide attendance certificates for ECU validation. It looks like we have quorum, and here's how folks have responded on the topic. Good. And then our second question is, how familiar are you with the equipment grounding conductor program? And this was a new one on me, so I'm anxious to see what's in the works. Just as a preview, there's a lot of material that Mark is going to be covering today, and we may or may not have time for questions on the broadcast, but be sure to use the question entry form because anything that we're not able to get to, we will respond to the group with a Q&A email. So it looks like we have a quorum here. Thank you for participating. And it looks like we're all in the same boat. So I think we're in the right place. Excellent. We've been able to include Mark in the presentations before. He is the significant contributor to the EasyPower webinar series, and he is the Standards and Application Engineering Manager at Littelfuse. If you give me a second, I'll hand the baton over to Mark. Mark, you can share your screen.
All right. Well, thanks, Jim. And thanks for the introduction, and thanks everybody for joining to learn a little bit more about special purpose GFCIs. Okay, yeah, so Jim gave me a basic introduction. I've been with Littelfuse now for 15 years, based in Western Canada, working with a lot of customers, you know, in the heavy industry primarily, but done a lot of work with ground fault protection and some of the other types of system protection. But really great to have everyone here to learn a bit more about the GFCIs. So, you know, to dig into this, it is helpful to just pause for a little bit and start with a little bit of background about GFCIs in general. So I've tried to split the presentation here into, you know, 4 general sections. So after an introduction to GFCIs, start talking about what's different, you know, about the special purpose GFCIs, and then how they are implemented into a system, and then talking a little bit about looking forward, you know, what can the industry do to continue to march forward and, you know, create more and more safer electrical systems. So without too much further ado, I think we can jump in. So if you've done any research on shock or any of that background, you know, the name Dalziel, you know, surely has come up. So just a bit of background here. You know, after some time, you know, working at General Electric and San Diego Gas and Electric, Dalziel, he went back into academia, UC Berkeley in 1932, to get several additional degrees and teach courses in power systems as an assistant professor. And while he was there, a colleague actually asked for his help designing a device to deal with some barn flies in order to electrocute them. And this research project certainly snowballed into something a lot bigger as he realized, the physiological effects that really small amounts of current could have on living creatures. So, the barn flies led to livestock, and then livestock led to human beings. And after a fair amount of research and experimentation, he developed into, basically the de facto world authority on that subject matter. And his expertise was really widely regarded and was consulted in a lot of electrical incidents and fatalities and doing that investigation. So the realization that these shocks and fatalities were caused by ground faults on common household circuits led him to the creation of that first ever GFCI in the early 60s. Now, human testing, of course, is no longer considered acceptable, which is, for very good reason, but it means that this data is still used as a basis for much of the shock protection requirements that we have today. So the research and his observations led to the development and inclusion of this data within a number of standards, IEC 60479-1, IEEE Standard 80, as well as the basis of the GFCI performance standard, UL 943. So it really led to those, the basis for a lot of those standards. Now, some of the basic observations are that, the lowest let go thresholds, that's your ability to let go, occur around 15 to 100 hertz. And it's actually a little bit higher at the DC and higher frequencies. Second, that the affecting your ability to breathe, you're dealing with your heart and serious damage to the nervous system did require shocks of greater intensity than those required to just produce ventricular fibrillation. So accidental shock currents, if they can be kept below the fibrillating threshold, the probability of death can be, significantly reduced. Another point in his research was that longer durations of shock were, of course, far more hazardous than a quick pulse of shock. And quick pulses were less likely to cause that ventricular fibrillation. So Dalziel was able to develop equations based on a function of a person's weight to define what a human body can tolerate without causing that fibrillation. And the UL curve that goes into the GFCI standard is actually based on those equations. There's other factors, of course, dry skin being a better insulator than moist or sweaty skin, and cuts, or other perforations of the skin can also have a significant effect there. The path through the body that was on that previous slide, of course, also impacts whether the current goes through, just whether it goes through your heart or whether it goes through other tissues in your body. So that also has an impact on that. Now, this data shown on the slide here right now, this is taken from that IEC 60479 standard, which is based on Dalziel's work. And this just really shows how the current and the time both play a factor in the severity of a shock injury. So when you add, the extra information here, you can see the ranges go from, what's labeled as, imperceptible up to fibrillation. And really what I want to highlight here is that line between AC2 and AC3, where it goes from no immediate, damage to the body to beyond the let go threshold, which is the involuntary muscular contractions. That line is not straight up and down. There is an angle there, which says there are some current levels that could be present on the body for a certain amount of time before you end up with that inability to let go. And there is a definite line where the B hits the top of the graph, where if you need to stay below that let go threshold, the current needs to be below a certain value. So this is just something to remember as we keep talking about some of the other slides. In particular, the standard household GFCIs trip at 6 milliamps or below, and this value is not selected by accident. So just as I mentioned, we want to, with those Class A GFCIs, stay below the let-go threshold, which is why that value of 6 milliamps was chosen. Now, after that risk of shock was, we'll say, quantified and better understood, that really made it possible for companies to develop products that could detect these currents and de-energize the circuit quickly in order to provide that protection from shock. So since the introduction of those GFCIs in the residential setting, there's been over an 80% drop in residential electrocutions and over a 95% drop in consumer products electrocutions. So the graph is pretty obvious to show, as time has gone, the number of overall electrocutions falling steadily and dramatically, despite the number of homes increasing. But as the GFCIs proliferated in the home, the green curve, as they were begun to be installed in all the new construction, there's a fairly strong correlation there. Now, it's true that appliance design has also improved. Other techniques such as double insulation have also assisted with reducing the electrocutions, but there's certainly no doubt that GFCIs have played a very leading role in this reduction. So although this is talking about residential, I think if you stop and just consider that impact, it's pretty amazing, that since 1970 compared to today, there's almost 1,000 deaths that are now prevented every year. And that's a lot of families, a lot of people that have the benefit of these safety technologies coming into play. So for most of its existence, the GFCI, whether it's receptacle type or circuit breaker type, as shown in those pictures there, it's really been focused on 125 volts, single phase circuits around 20 amps or less. Now, these requirements have recently started to expand in the electrical codes, specifically in the non-dwelling unit section of the code. And this is really recognizing the fact that shock hazards are not limited to those 125 volt, 20 amp circuits. So the three-phase receptacles, higher amperages, they certainly pose, similar shock hazards. And as three-phase voltages and higher amperage circuits mostly exist in non-residential applications, that's why the non-dwelling unit section of the code is what is being updated with some of this information. So what I'm highlighting here is just a couple of recent changes to show this advancement. So the 2017 NEC brought in a clause that expanded the requirement for GFCI protection to run up to 50 amps single phase and up to 100 amps for three-phase circuits. And I've put in bold a few of the areas there where there's more frequent use of plug-in cord equipment that hits these ranges. So kitchens, outdoor areas, garages, that's where we see some of this equipment. So just to pick on commercial kitchens for a moment, this just shows a few of the types of circuits that you might see where these amperages do exist. So it's equipment such as fryers, mixing equipment, electric ranges, and things that are movable in order to be able to meet sanitation standards. When you do that moving of the equipment around and connect it with plug-in cord, that's where those GFCI requirements come into play. And that's specifically because flexible cords are prone to wear and tear over time as you're moving it around, and that worn insulation really does increase the worker's risk for electric shock. Now I show that pin and sleeve connector there as well, so that when you look at three-phase receptacles, once you go above 60 amps, now like the code is requesting, you may need to use a different type of receptacle. And so these IEC-based pin and sleeve devices are often used for some of those higher amperage types of equipment. And on a similar note, in NEC 2020, there wasn't a major change, but there was just a minor update. And what I've highlighted there is to show, now instead of just a kitchen, it's now including areas that have a sink and permanent, food preparation. So this really expands that requirement to things like, we'll say ice cream parlors, coffee shops, areas like that, where they might have that high amperage equipment, but may not previously have qualified as a full, kitchen application. So again, we're still talking about, we'll say, the standard GFCIs, but I think it's important to give a little background about the GFCIs in the code today. And finally, on that note, the one last reference I want to make is, section 422 of the 2020 NEC talks about GFCI requirements for appliances. And in the 2020 cycle, dishwashers were added to this list. So three-phase devices that were 60 amps and below are now required to be supplied by a GFCI circuit. And the significance is that this is not just the plug and receptacle connected equipment. This is also for hardwired devices. So that's in recognition of really those specific risks that are posed by these kinds of appliances where there's a lot of water and, of course, people dealing with them all the time. So all of these requirements that are in the code today, what type of GFCI is that? And so if you look at the definition in the NEC or in the Canadian Electrical Code, the definition of the GFCI that's in there today has really focused on the Class A GFCI. So, it's true that when we talk about GFCIs, everyone automatically thinks of Class A GFCIs. And, that makes sense. That's what's been listed in the definition. That's what we've talked about in the past. Now, the Canadian Electrical Code does separate the GFCI term from a Class A GFCI. So there is a little bit of separation there, whereas in the US, the NEC has really considered those one and the same. So let's just take a second to say, well, what is a Class A GFCI? And as I've mentioned, that's really tied to the UL 943 standard, which talks about a 6 milliamp trip level and a device intended for 150 volts line to ground or below, which you can read as essentially a 240 volt or less application. Now, one very interesting change in the world of GFCIs is set to occur next year. So special purpose GFCIs, they've been defined for some time, but they're now on deck to be added to the 2023 electrical code that is still in the works. Now, these comments have passed second draft. They still do have some steps to complete, the NEC code cycle process. So I have a disclaimer we'll say at the bottom there that, until it's final, it's not necessarily complete. But at the moment, special purpose GFCIs are scheduled to be added to the definitions as defined by the UL 943C standard, with 2 areas having a mandate to use them, one being Article 680 for swimming pools and fountains. So having equipment there wherever GFCIs are currently used. If you're using a 480 volt equipment in that similar application, the requirement will be to have a special purpose GFCI used with that equipment. And same for horticultural lighting in 410. So this is really going to, we'll say, raise the profile and bring special purpose GFCIs onto a lot more people's radar. So on this slide here, we're trying to put a bit of a simplified flow chart together to explain the different classes. And we'll kind of go into a little more detail as we go through. So we've talked about Class A being defined by UL 943, and 943C is a document that was put together about 10 years ago and defines what classes C, D, and E are all about. So these devices are still subjected to the 943 tests underneath, but just have a few different parameters that are defined in the 943C standard. Now, one of the main defining factors is the system voltage. So for systems that are above 240, and we'll just say, 480 volts is a good example. That's the standard industrial voltage in a lot of the US. You would move to a Class C special purpose GFCI. And for systems that are above 480, and here I'm looking at, we'll say 600 as the industrial voltage in Canada, then that's where a Class D special purpose GFCI would fit. Now there's some additional requirements here that we'll unpack in some of the upcoming slides. But that's really, the voltage is your first determining factor. Now, we'll say the second thing to look at is your trip time. So the Class A devices, as we've talked about, have that 6 milliamp trip level. That means they provide that let-go protection as well as ventricular fibrillation. Now, the Class C, D, and E, the special purpose GFCIs, have a 20 milliamp fixed trip level. So if you remember back to that, some of the curves we were looking at, this does provide ventricular fibrillation protection, but is not going to provide complete let-go protection. Now, because these devices are intended for use on industrial applications where that higher voltage equipment is used, that slightly increased trip level was really required for stability. So these industrial power systems can have leakage currents that can sometimes exceed that 6 milliamp trip level, especially during some types of motor and pump startups. So this really varies, we'll say, wildly depending on the equipment and the site. But as a general statement, that 20 milliamp fixed trip level provides that slightly higher level that allows the device to be more stable in an industrial area. Now at the top, I've drawn a line to a box there showing a formula that 20 over I to the power of 1.43. That is the curve that UL uses for 943 for the Class A GFCI, and the special purpose ones follow the same curve. So this is the curve here. So this is an inverse time curve that essentially means the time that the device is required to de-energize the circuit depends on the magnitude of current that's being measured. So it shows the data point on there for a 6 milliamp trip level, as well as the 20 milliamp trip level. So they're following the same curve, and at that slightly higher 20 milliamp level, the device has to operate just a little bit quicker, to be within that curve. And we draw the white dotted line at that anchor point, which is a minimum point there, that anything above 300 milliamps, the GFCI has to trip in less than 20 milliseconds. And that's true for all of those, GFCIs. So the Class C and D devices have to do the same thing as well. The EGFPD stands for Equipment Ground Fault Protection Device, and we'll talk a little bit about that at the end of the presentation. And it's essentially a device that has to follow similar trip settings, or we'll say similar trip curve requirements, but has an adjustable setting. But because it's adjustable, it cannot be called a GFCI. So there's some specific applications in the code where that device is used, and we'll talk about those. Now, the reason I want to show this briefly, if you recall that inverse time curve we were just looking at on the slide before, you can imagine how that kind of sits right here across that angled dividing line, that dotted line B. So that inverse time current curve selected by UL really tries to fit in here so that these GFCI devices can ensure that we're protecting against, fibrillation and providing the best protection we can. So I didn't try to overlay it specifically on this curve, but you can imagine how it might fit there. So the 20 milliamp level, you can see I've tagged it at the bottom of the bottom axis. It is able to provide fibrillation protection, but it's not able to provide complete let-go protection. That's what's provided in the Class A GFCI. So there is that one trade-off there. So aside from that 6 versus 20 milliamp trip level, what are the other unique parts of a special purpose GFCI? And there's really two main things to talk about here. The first one is ground continuity monitoring. So I don't really need to read, the sections of the code there that are coming from that 943C standard. But the important point is these special purpose GFCIs, so that's Class C, D, and E, they have to monitor the grounding circuit. So that is the ground from the load equipment back to the special purpose GFCI, and make sure that that grounding circuit is not open circuit. So the device has to actually de-energize if it senses an open circuit there, as well as a high impedance circuit that could cause an unsafe voltage drop across the grounding circuit. So this is something that's mandatory for these special purpose GFCIs to do. Now, the reason that that's included is if you just look at a typical setup here where you have a distribution panel going to a special purpose GFCI in this case with a receptacle, and then you have a flexible cable out to a load. So in this case, we have a 3-phase welder. Now that cable, where I have the green arrow on there, it could be subjected to a lot of abuse. Maybe it gets stretched and pulled around corners, gets driven over, gets pinched. Maybe those couplers get, banged around pretty hard. That cable can take a lot of abuse. Now, any failure of that ground path, that ground conductor in that cable could create additional voltage or unsafe voltage on the frame of that welder. So the job of the special purpose GFCI is to make sure that that low resistance ground path exists. So if we just put this into a simple schematic form and use your trusty V equals IR, it's pretty easy to see that if in the ground circuit you have a high resistance and then you get a phase to frame fault inside your load, you now have fault current going through your ground, and if you have a high impedance there, you end up with voltage drop across it. And in the worst case scenario, if you have a complete open circuit, now the issue is you have no fault current coming back to the special purpose GFCI, so it's not even able to see that fault current, but the frame of the equipment could be energized and cause a severe shock if somebody touches it. So this is the, we'll say, the reason why this is added as a requirement. Now, the one point I'll make, the reason that it was added to special purpose GFCIs and not for Class A is that the higher voltage involved with Class C and D make this problem a higher risk. So, and we're not going to get into, we'll say, portable GFCIs that have other requirements as well, but just at a high level, that voltage does present that risk. So it was seen as something that needed to be mandatory. So aside from the ground monitoring, the second item is the ground conductor sizing itself. So Class D in particular, so these are for 600 volt applications, they actually require an oversized equipment grounding conductor to be part of the installation. And this goes to what we were saying, what I was just saying on the previous slide. Again, as the voltage gets higher, you get more potential for voltage to be on the frame of the equipment based on the resistance of your grounding circuit when you have a ground fault. So when you have somebody touching the frame, you know, you maybe hear people talking about ground takes the path of least resistance. Well, that's not, we'll say, totally true. It takes all paths in proportion to their resistance. So it becomes, as the voltage gets higher, it becomes more and more imperative to have that very low resistance grounding path so that anyone who did come into contact with an energized frame would have as little current passing through them as possible. So what does the standard say? So UL 943C gives you a formula to calculate that resistance of the grounding conductor, and Appendix A goes through an example. Now, I think it's just important to mention it, but we're not going to go through a full example here today. And finally, Class E, special purpose GFCIs, have one additional requirement of their own. So Class E would be a 600 volt system that is not employing that oversized grounding conductor. And so in this case, because you don't have the extra assurance of that low resistance, you have to adopt ultra high speed tripping above 300 milliamps. So the formula, again, I've showed it in the box there in the middle, that 20 over I to the power of 1.43. That's, we'll say, the standard GFCI curve. With those Class E devices, once you go above that dotted line, above 300 milliamps, you have to trip at under the new supplied formula, 6.3 over I. So as an example, at 500 milliamps, that's a complete detection and clearing time of 2 milliseconds, which is extremely fast. So that's a specific requirement for Class E systems if you're utilizing, standard grounding without the additional sizing. Okay, so having talked a bit about the background and at least at a technical level what those special purpose GFCIs are, how do they work in the system and how do they fit into an existing system? So a three-phase special purpose GFCI really operates, in terms of the ground fault detection, the same as a Class A GFCI. So it uses a current sensor to detect any fault current that is returning back to the power source through a path other than the phase conductors. You can follow the steps shown here, but once somebody makes contact with an energized circuit and that leakage current does flow, the current sensor can detect that unbalance and the control circuit opens the fault within the specified time. So this really is the same for, this theory of operation is similar for all the standard GFCIs. Now, when we go to Class C, D, and E, the special purpose GFCIs, there's one additional, number 4 that we're adding here. So this is that grounding monitoring circuit that we just talked about a little bit. So what we're trying to monitor, you see this, the green, we'll say bond or earth conductor that is shown at the bottom here. We need to make sure that that is intact and that in fact has a low impedance as well, because we want to make sure that the panel itself on the load would have as low a voltage as possible during a phase to frame fault. So the blue conductor that's shown at the top is a pilot wire that we'll talk about just in a little bit, because that is how that ground monitoring is accomplished. So if you look at the zoom in here, and I'll show a little bigger picture in a second. Typically, this ground monitoring or ground measuring circuit is accomplished with the addition of a pilot wire. That's an additional conductor in the cable, and therefore would be an additional pin, in the couplers that you're using as well, in order to provide a loop, a circuit loop that you can use for a measurement. And that allows the special purpose GFCI to take a measurement of that ground return resistance. Now, the 943C standard doesn't tell you exactly how to do it. There's different methods depending on manufacturer that can be used. It is possible that you could use a terminating device at the end. It's also possible to not require that. Really, as I mentioned, the requirements there are just to detect an open grounding circuit or to detect a high impedance. So the way that the special purpose GFCI does that is by creating that loop with the pilot wire and having that connected to the ground return circuit on the load. So it's measuring the impedance of that loop. And if a terminating device is used at the end, there may be other features that can be added. One of those could be to detect an accidental pilot to ground short. So if you have a terminating device you're expecting, but that gets shorted out, you know that there is an issue with the cable somewhere between the load and the power source where the special purpose GFCI is connected. So that is something that could be added, but it's not a requirement of the standard. So in case you haven't seen too many of these, now this cable that has the pilot wire can come in many different shapes and sizes and forms. Some have multiple pilots as well. So don't get thrown off thinking it has to look exactly like this, but this is just one example. And I'm also showing where the pilot pin is sometimes installed in these type of couplers. So here the pilot pin is in the center. And in this case, you can see the pilot pin is the shortest, and that's really by design. That's not an accident. So if you imagine somebody disconnecting the circuit under load, which of course would not be advisable, that pilot would break first. And if you remember this diagram we have on the previous slide, as that pilot opens, it becomes open circuit, which would then trigger the special purpose GFCI to then de-energize the system because you now have an open circuit in your monitoring path. That is the shortest pin by design. So it's break first and make last. Now, one other benefit with the ground monitoring is that when the coupler is disconnected, so here you have a receptacle on a wall perhaps, if you have no coupler connected into it, because the ground monitoring loop would be open, then the GFCI would be required to keep that receptacle de-energized. So one, we'll say, side benefit is that the ground monitoring provides automatic de-energization of receptacles that might be on the wall when a load is not connected to it. And one final note on the ground monitoring part is that Of course, it's not anything that's mandatory for the Class A GFCIs, but it's also something that could be used if someone wanted to implement it. So there's no restriction in the Class A GFCIs against using the ground monitoring. So again, there could be some types of equipment, and here we show a fryer that could benefit from that automatic de-energization of the receptacle. Okay, now one of the questions we asked at the beginning was about the Assured Equipment Grounding Program, and this is in the same vein of what we've just been talking about. So the ground monitoring circuit is to make sure we have a low impedance ground, which is the same goal of this program. So this is part of, it's an OSHA program that has connections to the NEC in 590.6, that for construction equipment, that we need to do a physical inspection of the ground, prior to use every day. And so this is something that it's a manual procedure trying to verify that the ground is healthy before you're utilizing the equipment. Now, if you have a special purpose GFCI application, it actually takes care, or eliminate maybe is not the word some would use, but it takes care of the same steps, because it's proving that the ground is there and that it has a low impedance. So it's really doing this in an automated fashion. And so it takes care of the assured equipment grounding, meaning that you don't have to do all those steps manually. So if you're using that program on some of the portable equipment, perhaps in construction sites, a special purpose GFCI actually would take care of that in an automated fashion. Okay, so I want to switch gears just a little bit and say, okay, special purpose GFCIs, we've talked a bit about them, but how are they different than a ground fault relay that you might already have in your industrial system? So here we just show a ground fault relay connected to a current transformer. It operates sensing fault current in the exact same way that a GFCI does, but here the sensor and the ground fault relay and the circuit breaker are all individual components, potentially all from separate suppliers, that all have to be connected together. I mentioned EGFPD early on in the presentation. Now, this is a specific type of device for protection of equipment, but it does have sensitive trip levels. And there's some specific applications for it in the NEC related to de-icing and snow melting equipment. And they do have adjustable trip levels. They have to follow that same UL trip curve, so they are sensitive trip levels, but they are adjustable, and so therefore are not, GFCIs. Except in Canada, because the standard is a little more open with the wording, it actually can be certified as a GFCI. It doesn't meet the Class A, but it can be certified as a generic GFCI. Now, may also talk about GFPE, or ground fault protection of equipment. And so this would be the standard ground fault devices that you might have in an industrial circuit. So on a system, in NEC section 230.95 is where it talks about this. And really it's often set in terms of, amps or tens of amps or hundreds of amps. And the product category here is under UL 1053. So these, are paired with circuit breakers. They really are, there'll be a lot of adjustable settings on these products as well, and tuned to the specific application. So there's a lot of flexibility there, but the trip ranges can go anywhere from the more sensitive range up into the, as I mentioned, tens or hundreds of amps. So the name really helps to differentiate that. These types of products are not intending to try to provide shock protection for personnel. They are designed to protect the equipment. So they're trying to reduce the damage to equipment when there is a ground fault, and prevent equipment from, burning down. So to kind of put this into a basic summary of, the overall GFCI category, which all include special purpose GFCIs and standard GFCIs together, really, what are the high level differences compared to the industrial ground fault equipment? So aside from the standard, really the overall difference is that ground fault relays, GFPE, they're designed to protect the system equipment and to limit that damage, whereas a GFCI is specifically designed with those trip levels to try to protect people from death or even injury where they could be exposed to that shock hazard. Now, ground fault relays in industrial settings, as you mentioned, they're very flexible. So they would be connected to different types of interrupting devices, could be breakers, could be contactors, could be other sets of logic. So there's a lot of flexibility in what type of control scheme is there. But when you look at the total clearing time of that fault, it really can be, variable depending on different types of circumstances and time delays from that equipment. So a GFCI, on the corollary, because it's designed for personnel protection, it's really meant to be as straightforward as possible, and so that people cannot go in and monkey with the settings and turn it out of range or make it so it's no longer effective at its protection. The GFCI products, and that's both for the Class A as well as the special purpose GFCIs, those trip levels are fixed. And the key part is that the entire unit, that's the sensing, processing, interrupting, everything has to be packaged together and tested as a package so you know exactly what you're going to get. And I didn't put it into this presentation, but the testing that is part of the UL 943 standard is very comprehensive. It goes through a lot of different function tests in all of the worst case type of scenarios. So it's really tried to make the product bulletproof so that you can rely on that protection. So to put this into a little bit of a table, it talks a little bit about just what I've already mentioned, but kind of puts it into a side-by-side comparison. So the one thing I want to highlight on this slide are some of the applications at the bottom. GFCIs, the Class A GFCIs, have been around for a long time. They've been fantastic, and they've saved countless numbers of lives. And there's a lot of code references, in both the National Electrical Code in the US as well as the Canadian Code. Now, I didn't include the Canadian references here, but if you'd like more information on that, please feel free to let me know and get in touch with me. But NEC 210.8 is the main GFCI section of the code in the US. Now, special purpose GFCIs, although they've been around maybe for almost 10 years, they are now finding their way into the National Electrical Code beginning in 2023, like I said, pending the completion of that process. So we're really going to begin to see those introduced into industrial circuits. So really think that's going to start making an impact on industrial systems as well. As we look forward, I want to talk a little bit about, I guess, the reason why special purpose GFCIs are important and why it's great to see them getting some recognition in the upcoming code. So if you look at the data around electrical fatalities, when you go back, decades, there's been fantastic progress at reducing fatalities. So this data here is from the US Bureau of Labor Statistics, and so as it's come down, over the years, you can also see that maybe the last, 8 to 10 years, it's really plateaued. So we have not been making progress in reducing kind of that baseline number of electrical fatalities. So that progress has stagnated a little bit. Now, when you dig into it just a little bit further, you can see that the non-electrical occupations are actually have a higher percentage, we'll say, are more likely to be involved in a fatal electrical accident compared to an electrical worker. And the construction industry in particular has the highest rate of those fatalities. So I think moving forward, when we look at those fatalities on the previous slide, the vast majority of these are shock. And so shock protection is something that we need to address, we'll say, as an overall industry, in order to make meaningful progress on reducing these numbers. And in particular, in the construction industry, is more heavily affected than others. And so that's some of the areas where maybe a good place to start. So there is a lot of information out there. There's a lot of great tools. It's really a whole nother presentation to talk about NFPA 70E and how to reduce your electrical risk, first by doing a hazard assessment, understanding the risk, and then by seeing what you can do about it. The topic of prevention through design or safety by design is really an important one to try to look at those risks that exist and what can we do to reduce them. And so focusing on the top half of this pyramid in the hierarchy of controls is going to be the most effective way of reducing it. So things like special purpose GFCIs would be an engineering control. It's not something that somebody has to remember to turn on, or that they have to, it's something that's there and will be actively protecting that circuit. Really, at the beginning, we talked about how GFCIs played an instrumental role in bringing down the number of electrocutions we've seen. And as special purpose GFCIs come into industrial circuits, I really think we may be able to make an impact of further reducing the number of fatalities we have. So the last slide, I want to make one small plug here with IEEE Electrical Safety Workshop. If you're interested with all the discussion about risk management and with designing a safety program, this is certainly an event that I'd highly recommend going to. I know EasyPower is also involved with this event every year as well. Just a small plug there to check this out if you are not aware of it already. It's a great conference to talk about electrical safety. With that, I'll finish the presentation. I know there's only a couple minutes left, so maybe see if there's a question or two we can try to answer, and then answer the rest of it.
There was a request for a copy of the slides. If you could send me a PDF copy of your presentation, we can put it on the same website as the video when it gets posted.
Yeah, that's no problem at all. I'll certainly do that.
And we do have, looks like about half a dozen questions that we'd probably better off doing a Q&A circular. So
sure, we can put together a complete answer and send it out to the group.
I want to thank you very much for participating today. It was a great presentation. I think a lot of us learned a lot. Thank you very much. Any other questions?
Jim. Thanks, everybody.
Any other questions, make sure you get them in as you're signing out. Thank you for attending today, and we'll look forward to you joining us in the future. Thanks a lot.